Hello, welcome to this recording of section 9.4, which is graphing rational functions. So just going to kind of go through, first of all, we'll just talk about analyzing asymptotes of functions. And that's really the first step that we're going to take in graphing rational functions, is taking a look at what their asymptotes are, and then you sketch those on their graphs. We're going to take a look at identifying asymptotes, and then how to graph a rational function using a table of values. So first off, a vertical asymptote, something we've seen before, is basically when your denominator of a function turns into 0, you would end up with a number divided by 0, which is undefined. So what that would look like if I had a vertical asymptote. If I had a vertical asymptote at like x equals 2, I'd go over 2. And what that means is your function would get closer and closer to that, but never touch. So that's what a vertical asymptote was, and those are going to have x equals equations. The horizontal asymptotes, there's a few different cases of them. So I'll let you read these individually, and then one of the specific cases is when there's no horizontal asymptote, which is when your degree of your numerator is greater than the degree, your highest power, of your denominator. There's no horizontal asymptote, but instead there's something that's called an oblique or a slant asymptote, and it's just a diagonal. So it's just a straight line diagonal coming across like this, and you're going to see a function get closer to it on one side, and then you're going to see something, usually we'll have a vertical asymptote, and you'll see like a curve on the other side. So there will be some examples of that where there's an oblique asymptote, and again, it just creates kind of a different looking curve. So what I'm going to do is go through a couple examples of calculating asymptotes. Once again, just kind of the picture. Horizontal asymptote is going to have a y equals equation because they're horizontal lines. Vertical asymptotes are going to have an x equals equation, and then an oblique asymptote is going to take the form of y equals mx plus b. So it's going to have kind of the similar format that we've seen of just graphing lines. So in this first problem, we want to determine asymptotes of this. First thing we're actually going to want to do is factor this. So I'm going to factor my numerator into 2x plus 3 and 2x minus 3. And I'm going to do the same thing with my denominator and look for multiples of negative 15 that add up to negative 2. And that would be x minus 5 and x plus 3. So the reason we like to do this is we're going to have to set the denominator equal to 0 anyway and solve. So factoring is not a waste of time there. But if we did have a common factor, we would cancel it out right now. So what ends up happening is we don't have a common factor. So I'm going to start off with vertical asymptotes. And what we're going to do is take each one of these values and set them equal to 0. So if I do x minus 5 equals 0, I'm going to have a vertical asymptote at x equals 5. And then if I take my other equation, x plus 3 equals 0, I'm going to have a vertical asymptote at x equals negative 3. So right away on our graph, I know that I could go over to where positive 5 is and negative 3, and I would end up with two vertical asymptotes there. So then the next thing that you analyze is your degree of your numerator. Highest power is 2. Your degree of your denominator has a highest power of 2. Now since your degrees are the same, there is a little formula that I put on the slide before this, which says if your degrees are the same, your horizontal asymptote occurs at m over j plus k. So we're going to look at m and j are what I'm deciding to call the coefficients of the x squared on the numerator and the denominator. The k value would be where my cursor is to the right. So we don't have a k value. What that would do is shift our function up or down, and we don't have a transformation like that. So I take a look at those coefficients, and I end up having a y equals equation. And you take the lead coefficient of your numerator, which is 4. The lead coefficient of the denominator is 1. So that tells me that I'm going to have a horizontal asymptote at y equals 4. And what that means is I could go up to 4 on my graph, and I would see an asymptote there. So if you threw this in your calculator, you would see like a curve here somewhere, you would see a curve up here, and another curve down here. It might be like a mirror image, I don't even know what it looks like. But basically your functions would get closer and closer to those asymptotes. And that's really the goals of this first section, is just to figure out what those are. And again, there's no oblique asymptote. That's the case where your degree of your top is greater than the degree of the bottom. This next example, I'll start off with factoring again. This time you can see that I do have this k value off to the side here, so that's going to come into play. But factoring this equation, my denominator is a perfect square, binomial, so I'm going to factor it into x plus 5 and x minus 5. So right off the bat, getting my vertical asymptotes, take your denominator and set them equal to 0. If I take x plus 5 and set it equal to 0, I'll end up with a vertical asymptote at x equals negative 5. If I set this factor equal to 0, I'll have a vertical asymptote at x equals positive 5. So since the degree of our numerator then, so this is kind of the next shift here, the degree of your numerator is 1, and that is less than the degree of the denominator. So on the note sheet, it says your horizontal asymptote occurs at the equation y equals k. And again, 3 is our k value, so it's as easy as really just saying y equals 3. Which again, on a picture, you'd have your coordinate grid, you'd have your x equals negative 5, your x equals positive 5, and then you would see a horizontal asymptote at y equals 3. That's really it as far as getting asymptotes. Nothing tricky, you just kind of follow those general guidelines of factoring your denominator, and then you're taking a look at degree. This example is just a little bit different because what you're going to see is that the degree of the numerator is greater than the degree of the denominator. So that's going to imply then that we have an oblique asymptote. And what you actually have to do is take the top expression and divide it by the bottom. Alright, so let me just kind of like say the bad news again. We have to take the top equation and divide it by the bottom. Now in this case, I would use synthetic division to divide. So I'm bringing back some prior knowledge of synthetic division. First, I'm going to factor this numerator and see if anything would cancel out. And I end up with 3x minus 4 times x plus 1 all over x plus 3. And where I got that factoring from is just a little, I used snowflake algorithm where I'd put my a value here. If I take a times c, that goes up here, and then my b value down below. So I end up with my factors of negative 4 and positive 3. So the 3 over 3 is where I'm getting x plus 1, and then here's my 3x minus 4. So this is the simplified version. Again, I will have a vertical asymptote, so I'm going to just knock that out right away. If I take my denominator and set it equal to 0, x plus 3 equals 0, I'm going to have a vertical asymptote at x equals negative 3. So now is the interesting part. What we're going to end up doing is synthetically dividing. So again, because the degree of the numerator is greater than your degree of the denominator, we are going to have this oblique asymptote. So if you threw this in your calculator, you would again see those curves where like you're going to see one curve coming like this, and you'd have another curve coming here. And what that implies is that you have this slant asymptote going across that is not horizontal and it's not vertical. So in order to get that slant asymptote, what I'm going to do is take the 3x squared minus x minus 4. So I'm taking the coefficients, the 3, the negative 1, the negative 4, and I'm going to synthetically divide negative 3. And just a reminder, if your factor is x plus 3, I'm going to be using negative 3. So the rules say I would just bring this straight down. Synthetic division says you would take negative 3 times the 3, which is negative 9. And adding going straight down, I get negative 10. Now this is the interesting part. I'll take it the step further. Whether I have a remainder or not is actually irrelevant in this case. Because all that we care about is this part right here, which implies that I would have 3x minus 10. Again, if you're taking something to the second power, dividing by something to the first power, that's where I'm getting this 3x from, and then the minus 10. That is actually your equation then of your oblique asymptote. Again, no tricks there. You just synthetically divide and take the main chunk of the function, and you're really neglecting the remainder. Because if the remainder was 0, that means that that would actually have been a factor, and we'd be able to like do some crossing out here, but that's not the case. So you're going to ignore the remainder and just take the other part from the synthetic division. But again, that is it. That's my oblique asymptote. I have no horizontal asymptote, and then I had the vertical asymptote at x equals negative 3. So then, very specific case of when I say we're going to eliminate a factor. If I had a function, for example, that said f of x equals x plus 1 times x minus 3 over x plus 1. If I had something like this, it's kind of interesting, but because this is a common factor, it would cross off, and you would really be left with x minus 3, which y equals x minus 3 is just a straight line. So you would start with your down 3, and you go up 1 over 1, up 1 over 1, up 1 over 1 for your slope, and your line would look like this. But the interesting part, because I crossed off that factor, x plus 1 equals 0, x equals negative 1 implies actually that I have a little hole in my graph at negative 1. So if you were to put the purple function, as it is, in your calculator, go to a table of values, you would see values for negative 3, negative 2, 0, 1, 2. You would keep seeing values. But at negative 1, you would get an error. And think about why that is. If I just go right back to the actual problem from the beginning of this, and I substituted negative 1 into my function, I would end up with a 0 here in for x. Or I'm sorry, yeah, you would end up with a 0 here because it'd be negative 1 plus 1. And you would end up with 0 over 0. Again, dividing by 0 gives us something that is undefined. And again, that's going to be what's called a point discontinuity, which we just call a hole in the graph. So we're going to encounter one of those throughout these problems. But as far as graphing these, we're going to start them off the same exact way. I'm going to get asymptotes for them. So first thing, I would factor your denominator here. And I'm going to end up with x minus 3 and x plus 2. And then I've also got this plus 1 that comes after. So right away on our graph, we can identify that I'm going to have vertical asymptotes at x equals, and it's the opposite of this, so positive 3, and the opposite of that, so negative 2. And we can draw those in right away. So go to negative 3 on your x-axis, where it's going to cross here. And that's one of our vertical asymptotes. And then the other one is over at x equals, oh wow, it was positive 3 and negative 2. My bad. Alright, here's my negative 2. Here's my positive 3. So again, those are the vertical asymptotes. So then I'm going to take a look at the horizontal asymptote, which since, again, go back to the rules, the degree of your numerator versus the degree of the denominator. Since the degree of the numerator is 0, that is less than the degree of the denominator, which is 2, and that implies that I'm going to have a horizontal asymptote at y equals our k value. Now, again, just pretend for a sec that we didn't have this here. You would just have a horizontal asymptote at y equals 0. But since I do have a k value, what that's going to do is shift our graph up. And we're going to, or actually you've done transformations before. So from section 9.3, transformation said if I had this value that came after, it shifted my function up anyway. So that is some prior knowledge as well. So again, this is my horizontal asymptote. It's at y equals 1. I knew where my vertical asymptotes were. So then it really comes down to using a table of values and graphing this function. And what I like to do is usually pick a couple points on both sides of these asymptotes, which I'm just going to skip towards the table that I have. This is right from my key. So these were the points from the table of values. You can see the asymptotes were drawn in. I roughly sketched the points, which you're going to get a lot of really ugly decimals on these things, and you kind of just eyeball it because what we're really looking for is really just the shape of these. Because in some cases, you're going to see the curves below on these sides, but you might see it above in the middle. So again, we're just trying to get an idea of this. I would say, again, going back to some of your prior knowledge, the larger that this numerator is, the more these points are going to be shifted away from that horizontal asymptote. Next example, and again, if you want to go back, pause, take that table down, take down the sketch, and then come forward. But I skipped over part B, and then I'm going to go right on to part C, which again, we're going to start off by factoring. My numerator is going to factor into x plus 2 times x plus 3, and neither of those cancel with x plus 4. So I'm going to identify, hey, I've got a vertical asymptote at x equals negative 4. So I'm going to go to where x equals negative 4 and draw in that vertical asymptote. And then what I'm going to do is realize that my degree of my numerator is 2, degree of the denominator is 1. Since the degree of the numerator is greater than the degree of the denominator, I'm going to have to, again, divide out these expressions. So I'm going to use synthetic division again, because now there is no horizontal asymptote. What we're going to have instead is the oblique asymptote, or what we call the slant. So I'm going to take the opposite of that factor, which is negative 4, and then take your coefficients of the numerator, which are 1, 5, and 6, and synthetically divide. So the 1 comes down, negative 4 times 1 is negative 4, 5 plus negative 4, or 5 minus 4 is 1, and then -4 times the 1 is -4. The remainder is totally irrelevant. This is the part that matters, which tells me that my oblique asymptote is going to be at y equals x plus 1. So again, slope-intercept form, I would start up 1 and go up 1 over 1, up 1 over 1, or down 1, left 1, down 1, left 1. And what you're going to do is draw in that dashed asymptote. So then this is the part where you're going to go to the calculator. Again, I'll put the slide up here, but what you would want to do is just pick a couple of x values on both sides of -4. And that would produce one of your curves down here. And then you're going to also see a curve coming up here. And they're going to be pretty tight to the corners here. I'll put up the sketch that I have in a second. But again, this was a case where we ended up, again, having to synthetically divide. And it's not always going to be that pretty. If your denominator was something like, if it said 2x plus 4, or 2x, let's just say plus 5, you would, I'd probably use long division if that were the case. And I wouldn't use synthetic division. And you might see an example of that. So here's the detailed version of the graph. Again, if you want to pause and take a look at this in detail, but if you do this in your graphing calculator, you'll see the curves as well, and they're just going to kind of hug the asymptotes. So last example that I'll go through, and this is an interesting one because when we factor it, you're going to see that I have a factor of x plus 5 on my numerator and denominator, which I kind of ran through one of these really quick already. But what happens is before you tell me that there is a vertical asymptote at -5, you have to factor. Like I said, you cannot jump to just setting the denominator equal to 0 right away. Reason being is this factor is going to cancel, and it's going to produce a hole at x equals -5. So then what we're going to want to do is graph the remainder of this, which is y equals x plus 2, and that's going to end up being my my function. So, or f of x equals x plus 2 rather. So I'm going to go up 2 for my y-intercept, and then go up 1 over 1, up 1 over 1, up 1 over 1, and I'm going to end up with a line that's going to look like this, except what I want to be sure to do is put in a hole at x equals -5. So I'm actually going to go back. I'm going to go to where 1, 2, 3, 4, -5 is, and again, you're just going to put a hole in that graph where that point would be. And again, I'll throw a table of values up here. And what you would see on your calculator is that error at -5. So here's what the table looks like. Again, if I did have something here at -5, you would see an error in your calculator, which implies again that you'd be dividing by 0, and it's really just an undefined value. So it acts kind of like an asymptote in a sense, where you're just not going to have that value in your domain, and that's why we remove it right away at the beginning of the function. So just going back and recapping all of this madness, again, the big key here was determining asymptotes. So these were the rules. Again, I feel like verticals are really easy. You set your denominator equal to 0. The horizontal one, you've just got all these rules, which I went through at least 2 cases of each one of these, where it comes down to factoring. If something cancels out, there might be a hole in your graph. And then again, if your degree of your numerator was greater than the degree of your denominator, that's where we had this slant asymptote. So there was the visual. We went through some of the examples of just finding the asymptotes, and then a couple as far as graphing the problems went. So if you want to go back and take down the tables of values and get a good sketch, you can do that.